All right, so it's 3 o'clock Central Time, and let's go ahead and get started. My name is Julia Matevosyan. I'm an Associate Director and Chief Engineer at Energy Systems Integration Group. I would like to welcome everyone to this ESIG webinar series. For those of you who's not familiar with ESIG, we are a membership-based nonprofit organization providing our members with objective information, resources, networking opportunities in support of clean energy and energy systems integration decisions. We do this through workshops, tutorials, webinars like this one, blogs, working group, and task force activities. And we are producing technical resource materials. For those of you who are members, thank you so much for supporting us, and it makes possible for these webinars and other work we do. For those of you who missed, we just had our spring technical workshop in Austin, Texas, the week of March 17th. As always, the workshop hosted a mix of technical content with additional focus on large loads integration. The workshop materials and recording are now available at the Spring Technical Workshop event page. So if you would like to see more, go to esig.energy events and find our Spring Technical Workshop. Overall, our workshops and monthly webinars are open to everyone, so please feel free to register anytime at ESIG website at www.esig.energy or find us on LinkedIn, YouTube, Facebook, and X. All right, just a few logistical matters before we get started. First of all, the participant lines will be muted for the duration of the webinar to avoid unnecessary distraction. For the Q&A, as always, please use Slido platform at slido.com. Enter event code ESIG8. The instructions are also currently at the bottom of the screen. You'll see a thumbs up button next to questions to allow us to prioritize and choose the questions in that order. We plan to save 10 to 15 minutes for the Q&A at the end and then wrap it up at the top of the hour. An email with a link will be provided once the video file has been posted, and we also plan to provide short responses to all unanswered questions for the webinar. So please don't be afraid to ask your questions on Slido. All right, to introduce today's topic, as grid transitions from synchronous machines to inverter-based resources, the grid services that power system needs will be stable, and the power system needs to be stable, will not change. But the way we define and measure those services will change. And it's more than just inertia service. This webinar will cover the Grid Stability Services framework that was introduced in ESIG Services Task Force in 2024, and will present results from applying the framework to quantified services on the current system. The presentation will also cover how those services change in high grid forming versus high grid following IBR futures, to enable planners and operators to determine how much stability services they have and what they need. The webinar will be presented by all-star crew here. It's Matt Richwine from Telos Energy, Deepak Ramasubramanian from EPRI, Nick Miller from HickoryLedge, Andrew Siller from Telos Energy, and Sushrut Takar from EPRI. So just a few more words about speakers. Matt Richwine is founding partner of Telos Energy and is a leader in power system engineering, power electronic controls, and system stability with over 15 years of experience. Prior to founding Telos Energy, Matt worked at GE Energy Consulting as a senior manager of the renewables and controls team. Nick Miller is internationally known power systems engineer with specialty in integration of wind and solar generation to bulk power systems. He consults and is currently conducting research on bulk and grid stability for US system operators and transmission owners. He spent 3/8 of a century with GE. He is an elected member of US National Academy of Engineering, IEEE Life Fellow, distinguished member of SIGRE, and lifetime member of ESIG. Deepak Ramasubramanian is currently Principal Technical Leader in Electric Power Research Institute, or EPRI. His work at EPRI includes development of new and improved mathematical models and processes for large electric power systems to represent the behavior of inverter-based resources, loads, and evaluation and development of transmission planning criteria, including uncertainty of sources and loads. Andrew Siller is a senior power systems engineer at Telos Energy. At Telos, Andrew uses power flow and dynamic stability models to study the reliability of power system. He brings experience in plant side controls and grid operations to the team. And last but not least, Sushru Takar is an engineer and scientist in the Transmission Operations and Planning Group at EPRI. His current research includes modeling, simulation of power systems with inverter-based resources, looking at different aspects related to stability and steady state and dynamic analysis. All right, so just a short reminder once again to use Slido at slido.com. With event code ESIC8 to ask your questions. And without any further ado, let's go ahead and get started. Matt, I'll turn it over to you.
Great. Thanks, Julia. And good afternoon, everyone. We're really excited to share an update of a really long-running effort now to quantify grid stability services, to really talk more specifically about what is it that we have and what is it that we need, and so we can better understand how that's going to change in the future. So let's jump right in. Just to set the stage a little bit more, the key questions here are what we're posing as these four are the key that we see for understanding stable operation at very high penetrations of IBR. And so what do we need? What services do we need? It's more than just inertia. There's a host of stability services. This particular question, there's been a lot of progress by the industry in defining what we need and talking about those, but largely they've been a qualitative nature. The other three questions is what we've really been focusing on and quantifying the amount of these stability services. How much? How much of the for each of these services? How much are there? How do we measure them? How do they change depending on different grid operating conditions? Second, how fast are they? Services work in different time frames. There's fast and slow, and of course, sustaining those services. All of it is needed. We need the fast, we need the slow, and we need it to be sustained. And where are these services needed and where are they provided? Location matters for some services more than others. I think we're accustomed to thinking about things like system frequency, and we think of that as a systemic service, and we'll see there are aspects that are both. And then there are other services more related to voltage, where of course location does matter. And so that's been another key pillar of this framework. And altogether, what we really want this to be is we want it to be a generalized technology agnostic framework that is systematically defined, that is repeatable. In other words, these services are defined in a systematic way and can be measured in a systematic way for anybody, for any grid doing this. And so it makes this analysis really repeatable and general for all. And something that can be rolled out to system operators and planners. A little bit more introduction. We're coming into this process. We're about a little over a year into this effort. And so I just wanted to refer to a few other things. We're not going to go through everything from the beginning, but we really want to share the latest updates and progress that we've made. So about this time a year ago, we had another ESIG webinar where we laid out the framework and we described that in more detail. There's a link here, and you can, of course, refer to that on the ESIG website. And so that gives a little bit more depth to some of the background that we're going to cover fairly quickly. We've also published a paper on this at the Wind and Solar Integration Workshop last year. We presented some updates along the way at the Fall Technical Workshop in Providence last year. And now we're here, and all the while we've been running the services task force. So there's a number of ways where we've been getting this information out and also taking feedback from a number of industry experts around the world as we've gone through. And where it's landing today is there's a report, kind of a rather extensive slide deck where I've just listed the table of contents, and it goes through all of the things that we've investigated and uncovered in our findings, and a great bit of detail. Today's webinar intends to take you through and hit the highlights of those and provide an overview of those. And so, we know that there's a lot of other work going on throughout the industry, This is really, we see as in addition to and complementary to a lot of the other work that is out there. So again, just to set the stage on the framework and provide a brief overview, we are looking at the framework in terms of a balance of a provision of services and a need for services, combined with that acceptance criteria for those services. And so on the provision side of the scale, that is primarily coming from resources. And we say resources as kind of that most general term, whether it's generation or other types of whether it's conventional generation, IBR generation, or assets like battery energy storage, and then also transmission for its ability to deliver those resources that are provided ultimately by the other resources. On the other side of the scale is the need for services. And here we're talking about the need for stability services. And so what constitutes a need for stability services? We'll talk a little bit more about that, but in short, these are the contingencies. So when you have a dynamic disturbance on the system, it creates a sudden need for these disturbances, or excuse me, a sudden need for these services. That, and combined with the acceptance criteria, which is another important piece of this. If your acceptance criteria, if your tolerances are very tight, that creates a strong need for having those services to control, for instance, voltage and frequency into a very tight band. Whereas if acceptance criteria is looser, it reduces some of the need for those services. And for this, we've defined it in 4 major pillars of services. And we'll just go through these briefly here. The power type, we're talking about services in terms of active power services and reactive power services. Typically for active power, we're thinking those are typically associated with frequency. And for reactive power, we're typically associated with voltage control. For the timeframes, there's fast timeframes and there's medium and slow timeframes. We've divvied this up, and in this effort, we'll mostly be talking about kind of the fastest timeframes and the slower timeframes. On the location pillar, there's the local or the regional aspects, and then there's the network-wide or the systemic aspects of location. And then finally, on the operations, a couple things that can affect the provision and need for services is how the system is being operated at any given time, in particular for the headroom of given resources. And so, for instance, if your resources are operating where they're all maxed out, for instance, and there isn't anywhere to go in terms of providing, for instance, additional active power response to an under frequency event, for instance, or additional reactive power, then you can be very much limited just in terms of the way that operating resources is, or how that resource is operating and dispatched. And so that's another aspect that we've taken and accounted for in this framework. So again, we want this to be a core idea of this is that it's technology agnostic, and that we're defining a level playing field, a functional specification of services that can apply to any of the resources that are out there, whether it's conventional or synchronous or inverter-based, whether it's battery, whether it's a non-energy resource like a STATCOM, all types of energy sources behind that, even loads, and whether the distributed or centralized, those aspects all fit into this framework. Transmission, again, a note on transmission, it's a little bit more indirect in terms of we consider the ability to move or deliver services to different locations, but not an inherent provider of services on its own. And so with that, I'd like to hand it over to Andrew Seiler to talk a little bit more about the location pillar of the framework. Andrew?
Everyone. Yes, as part of this project, we developed a grouping process to really capture that kind of locational column that Matt highlighted. The idea there being to capture the locational aspect of these services when we're characterizing them and trying to understand how they'll distribute throughout our power system. kind of a key objective as we were approaching this problem was to group buses within our power system, not just based on historical stability limits or ownership boundaries, but rather by the electrical attributes of the power system. An important note there is when I say electrical attributes, I mean both the transmission topology of the system as well as the characteristics of the resource mix. For example, when we're kind of starting our grouping process, we apply a short circuit fault analysis. So we take a bus in our power system and we apply a fault and we measure the voltage deviation at essentially every other bus in our test system. And so naturally that voltage deviation is going to be a function of the transmission topology, but then also affected by the resource mix and the amount of short circuit fault current available. We use that measure of voltage deviation to calculate an interaction factor between every bus in our system, which is essentially a measure of electrical closeness. The idea with this interaction factor is we're trying to understand which buses in our power system are going to exhibit similar dynamic characteristics and, in essence, swing together. The heat map that's kind of in the middle here shows the interaction factor for every bus in our test system, where red indicates buses with a very high interaction factor that are very close, and yellow and white are less close. In our grouping process, we applied a hierarchical method, essentially moving through the buses in our system and grouping the buses with the highest interaction factor first. The heat map in the bottom right shows the grouping that we ultimately used, which is kind of 8 core groups, where you can see they have relatively strong internal interaction with themselves, as indicated by the kind of the diagonal from the upper left to the bottom right, but then are relatively sparsely connected. The idea there being we expect these groups, when we run our dynamic simulations as part of this project, to swing together and remain kind of hang together. If we jump to the next slide, we can see these same groups mapped geographically. And so this is just another view that helped us understand and really contextualize the grouping as we applied it. You can see these groups vary quite a bit, both in the total generation resources available, as well as the penetration of inverter-based resources. The lines on this plot indicate the strength of the connection between the various groups and also indicate connections to the external system. So these groups will continue to show up throughout this presentation. This grouping process served as a useful framework for assessing kind of the locational aspect of these services. With that, I will give it to Deepak to talk about the resource characterization method that was applied.
Thanks, Andrew. So the idea for resource characterization is we wanted to go both top down and bottom up. Essentially, top down was kind of like the grouping that Andrew spoke about. Bottom up is now knowing what the existing resources in the system can provide and what can they do at a particular location, what can they do at a particular time instant, what can they do based upon the relationships of reactive power to voltage and active power to angle. So we wanted to get an idea of an individual resource. If you look at the few different time scales, so if you look at the very fast time scale, upon occurrence of a disturbance, let's say within 0.1 seconds, you look at a middle time frame where you're looking more at 0.1 to 2 seconds, where a lot of the fast frequency response kind of definition presently is in across our grid codes. And then you look at a slow time scale, we're able to get a characterization of what these resources can do in the existing system based upon their dynamic behavior. This individual unit response, looking at it You can take an entire case, and then we've developed methods to say that parse through individual plants, individual machines, individual resources. It can be load, it can be generation, it can be any other device. Parsing through them and get this kind of a response that goes across both time domain and frequency domain to get an idea of how these resources are going to react. We can then take that information and put it back into the grouping that we just described to then get an idea of a nodal level, zonal level, area level. How do things change with different kinds of change in inverter-based resource characterization or change in source characterization, get an idea of how the changes in the system are going to be impacted by the change of the resource. We can also get an idea of how potentially headroom is going to be impacting the ability of a resource to actually provide a particular response. We get ideas into dead bands. So you might have a lot of capability, but if dead bands are present in control, then you start getting an insight into whether a resource can actually provide a fast or a slow kind of behavior, depending upon what kind of dead bands might be present. So essentially, we looked at these three different time scales. You look at a fast time scale to get an idea of what happens immediately after a disturbance. You look at the middle time scale that you get an idea of what happens maybe after some controllers start acting, maybe after some measurement is done and some response is done. And then you get a slower time scale that gives an idea of more of plant level kind of responses. With that introduction, hand it over to Shushruth to talk a little bit about the individual resources and some nuances that came out from those characterizations.
Yeah, thanks, Deepak. Hello, everyone. So the idea behind this is really to get a quick and dirty look at what each resource may provide in these three fast, middle, and slow time frames. And for that, we set up the entire network, ensuring that any existing automations and in existing scripts are being set up correctly. And then we disconnect each of those resources and connect it to a single machine infinite burst setup where we apply disturbances, in this case, frequency domain, disturbance in voltage magnitude and frequency, and then measure the response in active and reactive power at that frequency. We have also looked at time domain disturbances, and the details are in the detailed report. But when we're looking at the frequency domain characterization, we look at three frequencies to get this idea. The slower time frame being about 10 seconds, so about 0.1 hertz, middle being about 1 hertz, and the fast being the first 0.1 second or so, which is 10 hertz. And at these three frequencies, we plot the active power versus frequency and reactive power versus voltage magnitude. And in this, it is important to consider the magnitude of the response, but also the phase of the response, where a phase of 0 might indicate that or a phase of 90 degrees might indicate that the resource does not respond to that disturbance, even if the magnitude is high, whereas a phase of plus or minus 180 degrees might indicate that the response is in opposite direction to whatever the disturbance was applied. So we just show three resources here: one synchronous machine, one wind turbine, and one grid following IPR. That seems to be following the active and reactive power command for the most part. And so in the active power sense, we see that the synchronous machine has a higher magnitude of response in the fast and medium time frame, whereas the responses are more similar between the synchronous machine wind in the slower time frame. Whereas for the reactive power, it is observed that in the faster time frame, the responses from all three resources are similar in terms of magnitude, whereas in the slower time frame, it is really again synchronous machine that has the higher response. Again, this for individual resource, things such as headrooms and any other nonlinear controls may not be captured in a linear frequency disturbance that we inject, depending on what magnitude of disturbance is used. But it should give us a good, quick and dirty idea about what each resource may provide in different time frames. And once we have the characterization performed for all the resources in the network, we can then combine them to get an idea on the zonal or regional level. And I'll hand it back to Matt to discuss more about that. Thanks.
Thanks, Sishrup. Yeah, I think, the great thing about this method is while there's time domains, while there's dynamic simulation, this is the aspect of dynamic simulation that's being done, but it's being done on a resource or a plant level basis. And some of the great work that the EPRI team has done here is they've taken it as you take in a complete power flow and dynamic database package, and the scheme can automatically go through and pull out the plant level, the plant level models, one plant at a time, and run this analysis and provide this characterization at the plant level. And so you sweep through a full power flow and dynamics database and do this for your region, and you end up with these resource characterization, these relatively simple plots for each plant level model of a very complex and large system. And from there is where we transition to kind of away from dynamic simulation and just processing and interpreting these results through the services lens. And so when we do that, now we start going line by every plant and looking at the resource characterization on its own basis and summing those up in engineering units, essentially, so that all of those responses within a given region can be summed up. And we get a view like this with a few different charts. Here we're showing on the top the active power services, and on the bottom the reactive power services. On the left we have the fast time frames, and on the right we have the slow time frames. And we've evaluated these. The colors of the different bars are the different, I'd say, large categories of the resources in the model that we were using. And so one thing that we can start with is the GFL types of resources, or the grid following types of resources, which we're referring to here as GFL category 1, which are kind of very legacy types of resources that don't have a lot of frequency, or voltage response. And so what you can see, what falls out of this analysis when you sum all of them up, is that there's very little provision of any of these services in the slow timeframes or the fast timeframes. And so you can see that by kind of the very small or marginal orange bars. On the other side, if we look at the synchronous machinery in blue, you can see that on the top left for the fast active power services, there's a large level of provision. And so when frequency changes, there's a large response in megawatts for those machines, as we all know and expect. When you look at that on the fast reactive services for synchronous machinery, you see there is a provision there, and it's moderate, but we know that and expect that from synchronous machinery because these resources provide inertia and kind of a grid strength or a voltage stiffness that is really being quantified by the plots by the blue bars in the left two plots. On the other side with the slow services, you see the synchronous machinery, you see a relatively small bar. And what's happening there is it's a little bit understated. The governor response, or the slower active power response, is a little bit muted because of the dead bands and the controls. On the reactive power side, you can see the effect of the excitation system responding to changes in voltage and providing reactive power to support voltage. And so you see that on the bottom right. The last category that we're looking at, category of resources, is the grid forming. And what you can see by the green plots is, again, starting back on the fast services. On the fast active power services, we do see a significant provision from the grid forming resources and its representation in the models that we are using for providing that response. When frequency or when phase angle moves, we see that response in active power. Similarly, on the reactive power side, we see that when voltage changes, there's a very fast response and reactive power to support and to correct that change in voltage. Again, that corrective action is important and is related to that phase angle that Sushruth was describing on the previous slide. Similarly, on the slower services, we see a robust response for the slow active power services, and also at the kind of the plant level voltage regulation response for those grid forming resources as well on the bottom right. And so looking at that, that is kind of the provision end of the scale and how those sum up. On the other side of the scale, defining the need for stability services. So we looked at this, we looked at two different disturbances that would constitute a need for these stability services. One is a generation contingency, in which for each of the groups that we had defined in the method that Andrew described, we would trip the single largest generator by megawatt output in the group. And this would constitute a demand for a lot of the services, but particularly the active power services, as this would result in a reduction in frequency and an immediate change of frequency declining. We also looked at transmission contingencies in each of the groups, being the trip of a single line or transformer with the highest flow, and these usually being internal within the group, again, constituting primarily a demand or creating a need for reactive power services. And so having defined all of this, we now shifted gears. So with the first bit, this is a lot of the work that we have done and a good bit of it that we presented out. And we wanted to see, okay, fine, but how well does it work? And so we moved into benchmarking the framework. And the idea for testing this and deciding, okay, are these things, these concepts that we've presented here, how do they work in practice? And so what we've done to benchmark it is, starting on the left, we graciously, SPP helped us in providing some of their transmission planning models and dynamic data sets for us to use and see how and to apply our framework and start to quantify these different levels of services. And so starting with that data, and again, this is data that is readily available to ISOs and TSOs generally. It's not something specific, and we're pulling it from the commercial software systems that are already in use. So it's pretty handy, should be pretty handy data. And we start by performing that regional grouping analysis in light blue that Andrew discussed. We also calculate the provision of services analysis that Deepak and Sushruth provided or explained in the green block here. And we also computed the need for services and looking at those generation and transmission contingencies. And with this, we we populated the scale, and in a sense, taking an inventory of the provision of services and weighing those against the needs for services. That is the framework application. On the bottom part, what we did is a more conventional stability analysis, where we took that same system and we applied those same contingencies that we defined in the needs for services, and we ran the dynamic simulations for each of those, and we compared the results of those time series dynamic simulations with the quantities that we were getting from the services inventory from our framework. And so those are the results that we're really excited to share with the team. But we did this for a few different scenarios and sensitivities. So again, we started with a relatively conventional case where there's a lot of there's a synchronous machinery dominant case that does consider a high load, a light load and a high wind case, where the IBR penetration is on the order of 60%. What we did was we then looked at a few other different sensitivities for this, where we substituted some of that synchronous machinery in the case for IBR resources, both represented as grid following category 1 resources, as well as grid forming types of resources. And again, to look at how different levels of provision of services via different types of control technologies would impact the dynamic performance of the system and how that would be reflected in our services framework. We also did, as kind of a teaser, we looked at a case where we added some transmission to see the impact. We have those results in our detailed deck, but unfortunately don't have time to share those today. And so again, getting back to our scale, our weighing analogy here of comparing the provision for and the need for these services. What we're looking at here is just zooming in to the fast active power services. So again, what we're looking at is for a small immediate change in frequency, how does active power change in those shortest timeframes? And when we look across our 8 groups, we see each of the different groups have a different profile, a different mix of resources, and each of those resources have different characteristics, which result in different levels of service provisions reflected by the bars in the left chart. And so you can see, for instance, group 6 has resources that constitute there's a lot of active power services available in group 6, and then very little in some of the other groups like 2, 7, and 8. And when you look at the resource mix, what we see in this case is that group 6 had a particularly large amount of synchronous machine resources, whereas group 7, 8, and 2 had more of the legacy IBR types of resources. And so what's falling out of the framework makes sense when you go back and look at the mix of what's actually in the dynamic database. Now we compare that again with the need for services and basically seeing what are the largest generation, what's the largest generation dispatch and the largest transmission lines in there. And you can see, for instance, in group 5, there is the largest single generator dispatch in there, which in this case constitutes the largest need for those fast active services, active power services. So when we look at, for instance, zooming in on groups 3 and groups 5, if we look at starting at group 3, we would say, okay, well, there's not a lot of service provision from those as indicated by the left chart. And then when you look at the need for those services, you see a need for services that's relatively low with respect to group 5, right? So when you look at these together, you say, okay, the need for services in group 3 versus group 5 is maybe about half. So maybe we would expect the performance to be better in group 3 and group 5 because group 3 has a less need for those services. It has a smaller generation contingency. But when you look at the provision of these services, you see that actually the provision of services is on par with the need for services, and that there is less provision of services in group 3 than in group 5. And so really what this gets to is, again, think of it hanging on the scale. It's the ratio of the provision to the need for those services. And if we compare groups 3 and 5, we see that that ratio is similar. And so from our framework, what this would lead us to expect is that the dynamic performance of the generator contingency, of the loss of generation disturbance in group 3 and in group 5 would look somewhat similar in the fast time frame. And so now we flip over and look at those large system dynamic simulations. and paying most attention to the fast time frame, or the first 100 milliseconds or so. And what we see here is, so we're looking at the first kind of 4 seconds after the disturbance in each of the plots. On the left is the plot with the loss of generation in group 3, and on the right is the plot of the loss of generation in group 5. One of the first things that we can see and that we call out here is looking at the rock-off, or the rate of change of frequency, for kind of the whole system, the system-wide view of it. And you can see that the rock-off for the loss of generation in group 5 is about twice that of group 3. And again, this is what we would typically come to expect in terms of that was a larger loss of generation that occurred in group 5. But when you zoom into the fast time frames, you see that the local aspects of this become a lot more salient. And you can see that the change in frequency, basically the frequency deviation in these fast time frames locally is very similar, and that it gets down to, again, about 0.002 per unit in each of the cases. And that we're seeing is consistent in terms of predicted by the fast active power service roll-up from our framework. Now, one of the things is to say, okay, so that ratio seems to be indicative of the dynamic, is indicative of the dynamic performance that we're seeing when you run the full system dynamic simulation. And so when we start, the power of this is when we start looking at these future scenarios and sensitivities where we're decommitting more synchronous machinery, either through retirements or just at different times of the day, these values and that provision of services is going to change, and we're going to be able to predict the ways in which that's going to change, the risks that we would see, and kind of that change in dynamic performance without actually exhaustively running the full system dynamic simulations. We'll be able to see it from this framework first and get a better idea of what we would expect when we ultimately do invest in those large dynamic simulations. So again, the other way we wanted to look at this is across the different technology types, and comparing the fast active power, and again, staying with the fast active power services. What we see is the provisions from our synchronous machine dominant case, our grid following dominant case, and our grid forming dominant case. And again, for each of the groups, you can see how the resource mix evolves in each of those groups. And you can see these trends are very similar to what we had shared earlier and consistent with the technology types. In terms of synchronous machinery provides a strong, fast active power service, again, conventionally what we would refer to as inertia, depending on the levels of synchronous machinery in each of these groups. As those are substituted for other resources, in this case IBR of either grid following or grid forming, you can see how that changes. And in general, it's there's a reduction there, but it depends significantly on the types of resources, even for the same quantities which we've fixed in these cases. So the install base, for instance, of all resources is the same in the blue, the red, and the orange. It's just the attributes of the resources have changed. And so now zooming in a little bit further to the dynamic simulations from, again, for benchmarking this and drawing out the resource characteristics by technology type. We look at the loss of generation, again, in our group 3 case, and we can see on the top left plot, the synchronous machinery synchronous machinery dominant case. We see the response there. Again, in the middle, from the grid following dominant case, and then at the bottom for the grid forming dominant case. And we've extracted a few key metrics, again, associated with the fast timeframes for the active power response. That being the common mode rate of change of frequency, and then what we're calling the local nadir, or that frequency deviation magnitude in, again, that very fast time frame. And what these results from the large dynamic simulations are showing is that these metrics are consistent with the level of service provision in each of these sensitivities. So for instance, what we see is the metrics indicating the highest stress to the system being a high frequency deviation in short time frames, and the highest rock-off shows in our grid following dominant case. Next on the improvement is the grid forming, and then synchronous machinery dominant case has kind of the best metrics and is also consistent again with the highest level of services provisions. And so we see that the trends from the time domain results are corresponding well with this framework. We looked at this again for group 5. Again, a larger generator, a different mix, but some similarities in terms of most of the service provision coming from synchronous machinery technology, and then others from, and then also looking at it from grid forming and grid following dominant technology. And you can see very similar trends there. Again, indicating that what we're showing with the services framework is also being reflected in the more detailed time domain simulations. So what does this mean? And through this process, there were a number of lessons learned that we've taken away. And among these, we really want to highlight most resources provide valuable stability services, regardless of technology. And I would say most resources at a utility scale, the transmission system, where you've got some degree of voltage and frequency response. Now, the key is which of those services, how much, and how much is needed at that location. So all of those resources, the mix of resources out there varies in terms of how much, what technology type it is. Some resources may be much slower to respond, and so they may not be providing services in those fast timeframes, but they can provide them in the slower timeframes. And that's important, in the framework accounts and captures the value of that. Whereas other resources can provide these services across all of the timeframes. And again, that's being captured, and that value is reflected in this framework. The second point here is that dynamic model quality is foundational and continues to be a challenge. Especially when you look at the real systems and the real databases, there's a tremendous amount of data in these, of models that are from different vintages, and some legacy equipment and models out there. And really making sense of that and making sure that you're understanding what's coming in, and that when you perform the resource characterization and tease out the responses from all of these dynamic models, that it does make sense given the technology and the vintage of the installation that's there. And so that's something for us all, I think we're very aware of, and something that we need to continue to keep an eye on and keep working to improve. The other big lesson learned that came out of this is the appropriate analysis in the fast time frames is tricky. I think a lot of the dynamic behavior, we're accustomed to looking at it, especially on large systems, over what happens over the course of many seconds to 10 seconds or so. And when you start looking at the faster time frames, with what's happening within a second, not all of the measured signals are what you thought they were. In particular, measuring frequency is one example of a signal that needs to be treated with great care, especially when you start looking at the faster time frames. That's something that we've had to work through here in this effort, and we feel we have a good understanding, and these plots that we've shared have a consistent application in terms of a consistent methodology in terms of how we're computing frequency, specifically in those fast timeframes. Not something that can be taken for granted here. But why are we focusing so much on those fast timeframes? It's because we see those as becoming increasingly important, especially as the grid transitions to higher levels of IBR, and we lose that the contributions from synchronous machinery that have generally been very strong in those fast timeframes. Looking ahead to next steps, we're looking to improve the data checking routine. And so the work that the analysis that Deepak and Sushrut described of taking a dynamic model and parsing it by plant and extracting all of the services, that's a really core value and effort as part of this process in terms of not even just for services, but also sanity checking and checking those dynamic models and making sure that what's coming out of those is consistent and realistic given a technology type. The other big aspect of the other big next step that we see here is establishing guidelines for acceptable performance. Here, what we've shown is that the benchmarking is checking out and that the trends are consistent. What we're seeing from the framework is consistent with what we're seeing from the dynamics, from the large system dynamics simulation. And that was really important to us to say, okay, this framework does make sense. It is working. It has predictive power. But we need to say, okay, as you're looking at the scales and balancing the provision for and the need for these services, what are the metrics that we should be looking for? What are the rules of thumb to say, how much of a ratio of provision to need for a given service do you need to be stable and to meet the acceptance criteria that's generally in place today? And so kind of illustrated with the scale and the meter reading on the bottom right, we really see that putting some numbers, we're now in a place where we can start to do this and put some numbers on kind of the stoplight of the red, yellow, green, and provide guidance to practitioners and users of this framework. And so as such, we're pursuing more regions for applying this framework and really excited to demonstrate and continue to use this and refine it. So where do we see this being used and in what cases? So just a few ideas here. Particularly in future scenarios, looking ahead with resource mixes and portfolios where there are weak pockets. For instance, places where there's either a concentration of inverter-based resources or in combination with few synchronous machines in that region. Identifying if there's still sufficient services in that local region, or basically looking ahead to see if there's a deficiency and where that deficiency is likely to be and under what conditions. To inform how transmission investments may be located to better deliver not just the energy, but also these stability services. For instance, from a region with a lot of services to a region with few services or a weak pocket. Also could be used to identify for potential plant retirements that will likely cause stability problems. For instance, if a large retirement, which is associated with a retirement also of stability services, do you drop to a threshold that you should be concerned about and look for ways to mitigate? This could also be used to inform where do you need more services, and for instance, grid forming inverter technology being one of those that provides a robust level of services across all time frames. Where and at what points in the future horizon and in what locations on the system would you get the most value for those additional contributions? And then on the bottom, saying, the grid, of course, now is extremely dynamic and becoming more so in terms of, it changing between day and night a lot with high levels of solar installation and even hourly in terms of just what the irradiance and wind profiles are doing. And with those different types of resources, providing different levels of services, even throughout a day, let alone looking over years and years of future horizons. And so we see an application kind of in the operations and in the ops realm for assessing how these services can change even within a given day. And so just to wrap up, this framework, it's a new way to evaluate the system stability risks and future needs in a way that we're not asking, well, is this a synchronous machine, or is that a STATCOM, or what type of grid, what type of IBR is this? No, it's really based on the functional performance of whatever technology it is, as represented through its dynamic model. In this way, we have a systematic application of criteria and of steps that is repeatable, so that we can take any database from any power system and compute these services metrics and determine where there are places that where there are needs and where there is, for instance, excess, where you might not need to worry about it for some time. And that it works for small systems and large systems alike. It's really important that this be able to scale up and evaluate the very large systems. And it's part of helping make that more manageable. That grouping by location was a really key component of making it manageable for the very large systems. This approach we see as being a lot faster than the full system dynamic simulations. And as such, enabling engineers to evaluate more futures and more operating conditions in a very efficient and effective manner, and to understand where the system risks lie and what can be done about it, and also at what point in time in the future they may become a problem that needs to be addressed. And the last point here is that while this is a new method, it utilizes existing tools and data. And so we see it as really applied in terms of ready to be applied to the system data that is on the tips of planners' fingers now. And so bringing this together, having an appropriate framework, enabling an efficient analysis gets us to an effective planning. So with that, I think we'll stop, and thank you for your participation today, and be happy to take some questions.
Thank you, Matt. We're at the top of the hour, but I'll let maybe like 10 minutes, maybe people can hang in there to ask a few questions, and then we'll take the rest offline. So the first question is from John Simonelli. It's a good one. What is the grouping process? The grouping process may have very different results during the transmission and generation maintenance periods, which can be 6 months or greater. How do you handle those variations? I think that's a great one.
Yeah, thank you. And please, others jump in. Andrew, would you like to jump in on that one?
Yeah, I saw that one in advance and it got me excited. Yeah, so that was something we're absolutely thinking about when we were putting together the grouping process. Obviously the transmission system and the resource dispatch can change greatly month to month, depending on what outages there are. And similarly, like Matt was saying, depending on the dispatch, can change hour to hour within the day greatly as well. And so when we were putting together this grouping process, we tried to design it in a way that was really, really repeatable, essentially saying this is a process that can be run in minutes, not hours or days, and allows the user to reassess the relevant kind of boundaries within their system, which could then be used to recalculate services or do something similar. I'll leave it to you, Matt, or anyone else who wants to jump in. That's mine.
Andrew, this is Nick. I'll just make a quick additional comment to that for John and everybody. And remember, this is this would apply, what Andrew just said would apply not only to, generator maintenance, but line outages and all of the above. So you can imagine, for example, one of those cells in Andrew's earlier slide breaking into two cells because of a significant loss of connectivity within what is otherwise a block, and that could very quickly advise, hey, you need to pay attention to the resources in each of these newly formed sub blocks for the maintenance period. So we think it's very powerful, that, and as Andrew keeps saying, repeatable. That's it.
And I'd like to also add, I think this is a really key, component. And John, thanks for raising this. One of the things is we arrived at 8 groups for a region the size of Kansas, right? As what we thought was kind of a good starting point, an appropriate level of aggregation of parts of the system, where the idea is that we don't want to make it too fine, and that now you have to evaluate all of these groups, and you're very sensitive to an outage or a specific contingency in terms of changing the groups a lot. But you don't want to have kind of a giant lump where different parts of that, aggregation actually are exhibiting very different dynamic behavior. And so part of it is finding the sweet spot and tuning what the size of those groups ought to be for a given analysis. We share where we think this one ought to be, but that process is completely tunable. And the algorithm that Andrew was describing can be adjusted to have either larger groups and more aggregation, or less, depending on a specific system and the needs and the contingencies that are known by the planners there.
Thank you. Let's go to the next one. What stability service is needed to compensate for grid phase jump angles, and how fast that service needs to be?
Great. Yeah, thanks. And again, team, feel free to jump in here. So the phase jump is a very fast phenomena, right? It's kind of infinitely fast, right? So what we see is the fast active power services in particular are the ones responsible for managing the phase jumps. And so, yeah, that's the short answer to that.
All right. What limits the fast active power response of grid forming versus synchronous machine? Is it the amount of stored energy available to it, or something else?
Great question on kind of the constraints and the headroom. Deepak, don't let me keep you from jumping in here too. How we consider this, so this is where the technology type does have an impact in terms of how the limits and constraints would be applied. For synchronous machinery, for instance, there's nothing that will limit the current during a disturbance necessarily. It is going to, and so for an active power provision in the short time frames, the synchronous machine is going to do what's governed by basically the equivalent circuit model of the machine, and it will deliver that provision. And the longer and the slow time frames, that response is dictated by the governor and the headroom and what the prime mover there can do. In contrast to IBR, and particular in grid forming, that's something that I think an aspect of this that we've considered, but needs more refinement. How we've defined it is that the IBR is assumed to, so for the fast time frame, that there's a very modest but hard limit applied on the grid forming, also the grid following IBR, because that technology and those power electronics have hard limits that generally are acting very quickly. Now, there's other discussion to say, okay, should there be some short-term overload capability in this technology? Some manufacturers may be offering that. That would be great. That could be reflected in this framework, but our assumption here is that that technology has a very hard limit. In the slow timeframes, particularly for active power response, what we're looking at is headroom, and we are assuming that what's behind that technology is like a wind is basically has no more room to go up. And so for wind or solar, it's run at the resource, it's uncurtailed. And for battery, we made an assumption that there wasn't any more power headroom available. But those assumptions are very material to the dynamic performance that you see. And so having an eye on that, we think is very important.
Yeah, and I think as Matt was saying, it's in those faster time scales, what differentiates an inverter from the synchronous machine is irrespective of what control type you have in an inverter, in those faster time scales, limits would still apply. So power limits, current limits, all of them still start being present. Whereas in a synchronous machine in that faster time scale, there's essentially no limit coming into play.
Last one more. Why wouldn't grid following IBR have substantial contribution to slow reactive power service provision?
I can take that one, Matt. It's
Go ahead.
the nuance there is it's category 1 grid following that we have considered. So category 1 grid following, as Matt mentioned, is the legacy inverters that operate at unity power factor and provide no other form of support. Now, the detailed report that we have does look a little bit into other categories of inverters that can provide different kinds of voltage support and frequency support services. But going into all of those categories in detail is to a certain extent some amount of future work that we have identified. What we've done here is look at 2 bookends, wherein one bookend on the grid following side assumes the legacy unity power factor operation of the device, and then you have the other bookend, which is the quintessential inverter for grid forming that can even do black start and things like that.
This is Nick. If I just might add a little color to that, to Deepak's answer. One of the nice things about this framework is, yeah, we can get you can get hung up on the labels, but the reality is the framework is technology agnostic and flexible. So up to the granularity of characterizing every individual resource, if you've got sufficient models, is reflected in the overall performance. You can call it what you want. You know, you can apply any label you want to a specific resource, but it will be reflected and evaluated on the same scale as every other resource. And when it, if it's out for maintenance, it ain't in there. If it gets changed out, the model changes. Very flexible and repeatable. That's all.
Right, I'll ask one last one because it's in a similar vein. If we categorize PFR response as slow active megawatt response, if resource have the same PFR droop setting, wouldn't they have same D megawatt DF value regardless of the type?
I didn't probably capture the full question, Julia. Could you, if there's time, repeat it?
So if PFR response is categorized as slow active megawatt service, if resources have the same PFR droop setting, would they all have the same D megawatt DF value regardless of the type of resource that they are?
Got it. Okay, so there's a difference between the droop value and the speed of the controller. So the droop setting in a resource effectively looks at this much slower time scale, which defines upon the settling values. Different resources can have the same droop, but they can have different speeds of control. It's not just for inverter-based resources, even for a synchronous machine, gas turbine versus a steam turbine versus a hydro turbine can all have the same value of droop, but they have different speeds of response. So we'll start seeing differences in the medium range. So in that 0.5 to 2 seconds range, we'll start seeing differences in values, but we may not see much differences in the greater than 2 seconds range.
Thank you. All right, so we are at the top of the hour, or we passed the top of the hour, and I will need to wrap up. I would like to thank Matt, Deepak, Nick, Andrew, and Sushrut for the webinar today. As I mentioned earlier, an email will go out once the video has been posted, and we'll answer all the questions that we didn't get to offline, and we'll post the responses as quickly as possible. We appreciate your engagement and look forward to seeing you again soon, perhaps at our next webinar on April 22nd, at the next ESIG webinar series. The webinar will be on gaps, barriers, and solutions to demand response participation in wholesale markets, and will be led by Derek Stanklick, also from Telos Energy, and will be followed by a panel of industry experts. The webinar will cover the key findings from the actionable recommendations from ESIG latest report on demand response. Further information on all of our webinars and meetings can be found at our website at www.esig.energy under events, in our newsletters and informational emails, and you are all invited to attend. Matt, Deepak, Nick, Andrew, Sushrut, thank you once again for this very timely informational webinar, and I thank you all for your attendance, and sorry we ran a little bit over time. We're looking forward to seeing you in the future.
Thanks,
Take
Julia.
care, be safe, and
Thanks,
goodbye.
everyone.